During this phase of the implementation, the project was completed. Similar to the previous phases, the role of driver, navigator, and design keeper kept switching over the course of the iteration. The tasks were divided between each team member, and the product backlog was successfully completed. A few changes were made to the UML diagram after the sprint review session. The displaying library was removed, and its functionality was merged with the tracking class. New functions were added to the tracking class, and the functionality of other methods was also changed a little bit. And the detect faces function of the detection class was updated to take frames as input from the video.
The detailed overview of the project is as follows. In this project, our detection library serves as the eyes of the robot in a way, enabling it to identify human obstacles through facial detection. First, during initialization, a robust detection model using OpenCV's net method is constructed. The DNN resident model has been used for doing the facial recognition. Then the init video stream method kickstarts a video stream, allowing us to continuously capture image frames from the monocular camera. Next, utilizing the initialized model, the detect face method scans each frame, identifying human faces. It meticulously evaluates confidence levels, ensuring only accurate detections are processed. Once the face are detected, the normalized coordinates of the bounding box are extracted and stored into the detect faces vector. A models folder was added which contains the .cafe model and .prototext file of the DNN resident model.
For the tracking library, first, the variables are initialized using a constructor. Then we have a find depth function, which will be used later to find the distance of the object from the robot. Then we have the assign ID and track method, which is used to assign unique IDs to any detected obstacle. So in the start, when an obstacle is detected and the IDs have not been assigned, this method will assign the ID. Then for existing IDs, in the next iteration, it will calculate the minimum Euclidean distance and assign the IDs correctly. If an object moves out of the frame, the ID will be deallocated. Now, when there are false detections in the center, for example, a face is supposed to be in the center, but it suddenly disappears, this is considered as a false positive and the ID will not be deleted. Then we have the method for calculating the distance from the camera. Here, the output will be the X, Y, Z distance in pixels of the obstacle from the camera reference frame. This method calls the find depth function. For the distance from the robot, or in our application from the car, here the XYZ distance in inches is calculated based on the distance from the camera, where a rotation and translation is performed.
For testing the implementation, the example code that uses the library is written. First, build inputs like distance, offset from the origin, and the camera field of view. Then a tracking class object is initialized and used later. An image frame is read using detection class, which is a member of the tracking class, and faces are detected. The bounding boxes are then assigned unique IDs, followed by distance calculation, and finally the outputs are displayed both in console as an image with a drawn bounding box to complete the working. Next, the demo of the working of the project will be shown. After the project implementation was completed, the Oxygen documentation of the files was written and the CPP check and CPP verification was done. Now, how about this image? How about this image?
So